We're going to start by doing a very similar problem to the last one in video 3.3.2. Find the average rate of change of this function in simplest form. This function here is k of x equals 4x minus 2. And we're looking at the interval from 3 plus h. All right, so again, we're going to use this average rate of change function, lowercase o. That's the function value at the second input minus the function value at the first input. The function here is k, f, g, k, h. You can name a function whenever you want. The function here is k, divided by the second input minus the first input. And again, this is our first input. This is our second input. So here especially, we're going to have to really be careful about parentheses. The second input is 3 plus h, so replace x2 with 3 plus h, minus the first one, which is just 3. As a side, well, never mind, I won't make that side note, divided by 3 plus h, minus the first input, which is 3. So now we have to plug these in. So we're going to go off to the side. And actually, I don't think parentheses are going to matter here. I lied to you. I'm sorry. I'm a liar. Also, I wonder if I could... It's almost the same color. I was hoping I could like draw an arm or something coming out of my shoulder here. And it would look really real. But I don't think it really does. Also, I have the right number of fingers. I just have a weird claw. It almost works, right? Use your imagination. Anyway, let's go off to the side. What is k of 3 plus h? This tells us what k is. We're replacing x with 3 plus h. So it's 4x. Oh, replace x with 3 plus h. Minus 2, like so. This is going to be very useful in 3.4 when we talk about function composition. Let's simplify this. Distribute. 4 times 3 is 12. 4 times h is 4h. And we have the minus 2. Combine like terms. 12 minus 2 is 10. Plus 4h. We also have to figure out what is the value of this function when the input is equal to 3. So again, go over to the function, replace all the x's with 3's. 4 times 3 minus 2 is 12 minus 2, which is just 10. And now we replace each of these with what they equal. This first function is equal to 10 plus 4h, minus the second function, which is equal to 10. Divided by the denominator, we have a plus 3 and a minus 3. The only thing left on the denominator is h. What happens on the numerator when we simplify? We have a plus 10 and a minus 10. Those go away. The only things we're left with is 4h on the top and h on the bottom. And as long as h is not equal to 0, we can cancel this out. We get the average rate of change is just 4. As long as h is not equal to 0. I'm not really going to make a big deal out of this. I'm not going to take off points if you don't include this. So if you're curious about it, we can talk about it, but otherwise it's not a too big of a deal. The average rate of change here is 4. So from the interval 3 to anything bigger than 3, the average rate of change is 4. And that's kind of cool if you really think about it. I'm going to nerd out for a little bit, right? Look at this function. What is this function? This function is 4x minus 2. This is a line with y-intercept negative 2. The average rate of change between any 2 points is 4. Because if I look at any 2 points, right, any 2 points, the rate of change is the slope of the line connecting those points. Well, any 2 points on the line is going to have the slope of 4, right? It's going to be the slope of the same line. That's how it kind of connects the secant lines and what's going on here. 3 plus h just means anywhere after 3. H can be whatever we want, anywhere after 3, which is kind of cool and why this problem is interesting. Let's do number 16. Number 16 says something. For the following, consider the graph of f, shown right here, and estimate the average change from x equals 1 to x equals 4. So average rate of change from x equals 1 to x equals 4. This is our first x. That's our second x. This c is weirding me out. Still kind of weirding me out a little bit. So remember, average rate of change, that's the function value at the second minus the function value at the first, divided by the second input minus the first input. So let's replace everything. Function value at the second input minus the function value at the first input, divided by the second input minus the first input. And then we go off to the side and say, what is f of 4? What is f of 1? Well, we have nothing to plug into this time. We need the graph, right? When x is equal to 4, what is y? When x is equal to 4, what is the y coordinate here? I don't really know. The y coordinate here is maybe 3.7 or something. I don't know. It's hard to estimate, but give your best guess. Let's say the y coordinate is 3.7. When the x value is 1, what is the y value? X value is 1. Whoa! I just did something. When the x value is 1, the y value is 5. So let's plug these in. This is what f of 4 is. This is what f of 1 is. Let's replace them. F of 4 is about 3.7. F of 1 is about 5. The denominator is 4 minus 1. That's 3. Let's keep simplifying. Subtract this out, negative 1.3. Divide that by 3. All right, this is going to be, let's approximate this. The average rate of change is whatever this is going to equal. I can't do this in my head. Yes, I can. It's negative 4.3 repeating, right? Let's check with a calculator. Negative 1.3 divided by 3. Yep. Oh. I was off by a decimal. That's why we check our answers. All right, so don't mind this. It is negative 0.43 repeating. This is our average rate of change. And actually, since we didn't round it, right, we use the repeating. We could actually replace this by a straight up equal sign, but it's not that important here. That's our average rate of change on this interval, which again, what this corresponds to, this is number 16. This says that if we drew a line from x equals 1 to x equals 4, a line between, oh, stop clicking, Jason. A line between these 2 points, it would have a slope. Oh, 4 is down here. Wait. Yeah, 4 is down here. I'm not losing my mind. Is that actually just across here? No, it's definitely down. We have a negative slope of about 0.4. Whew. I might be losing my mind today. Last problem, let's do. Problem number 44. Let's scroll all the way down. Ooh, a real world application. At the start of a trip, the odometer read 21,395. 21,395 at the start. It's good to write things down, write down the information. These are miles. And at the end of the trip, 13 and a half hours later, okay, 13.5 hours later, the odometer read 22,125. All right. And then, well, I wonder if I can do this. Oh, nope. Dangerous stuff going on right now. So assuming the scale is in miles, what's the average speed the car traveled? Well, let's go back to the very first thing. Now, there were a couple functions we used, or a couple ways that we look at the average rate of change. Average speed is average rate of change, remember. So there were a couple functions, but one of the ones we used was just the change in y over the change in x. You could use a couple different ones, but this right here, this is the change in time, our x. And our output right here, this is going to be related to the change. We'd have to calculate it, right? 22,125 minus 21,395. That's the change in y. You could also use the other formula that we've been using for everything. But this is another kind of perspective. So let's calculate that out. We can use Desmos if we wanted. 22,125 minus 21,395. That's a difference of 730 miles. So if we plug this in, 730 miles on the top, 13.5 hours on the bottom. And again, what are the units? Miles on the top, hours on the bottom. Type this into a calculator, it's going to give us our average speed. So 730 divided by 13.5, that's approximately 54.07. And what are the units? Miles on top, hours on the bottom, miles per hour. Anytime you have units, don't forget to include them. Okay. And that is how you do this application problem. That's how you find your average speed. Average speed is just an average rate of change. And in calculus, I said the C word again, the instantaneous rate of change, which is connected to something called a derivative, has to do with your instant speed, what your speedometer is saying at a moment in time. All right, good luck. Let me know if you have any questions.